we learned about or sometimes we just call this NMOS logic as well. And then we learn what we really like. We don't like this, bad crap. We like it, go away. But then we like this, right? This is CMOS logic. Check mark, we like that. But there's other kind of logic. And one other kind of logic that sometimes used, and we'll see where it's used later on, is what we call transmission gate logic, okay? And what is a transmission gate? Let's just back up here. So we know that if I make an NMOS switch, I'm just going to draw it upside down for now. Here's an NMOS switch. And what do we say NMOS are good at passing? If I want to pass something through to the other side here.
Low.
What's that? These are good at passing
A low value.
a what?
Low.
Zero.
A
Like-
low, yeah, a zero. These are good at passing the logic zeros, but not good for ones. But we know that PMOS are the opposite. They're good at passing logic ones. So I could, that's kind of how our inverter worked here, right? One was passing a logic zero. But we can connect those together like this. We have a PMOS and an NMOS, and we connect their drains and source together. And it's kind of like a double-sided switch. It's like basically we have a switch here and a switch here that we can pass 1 or 0. So the switches, we want them either to be open all the time or closed all the time, right? So there's two conditions. They're open or they're closed. So to do that, we have to connect them with the opposite signal. So if I call this signal A or whatever I want to call it, then this should be A bar, right? So when this is a 0 and this is a 1, both switches are open. It's like the switch being open. And when A is 1 and A bar is 0, both P and NMOS are turned on and the switch is closed. And no matter what this is here, a 0 or a 1, it'll pass good. If it's a 0, it'll go through the N. If it's a 1, it'll go through the P. And we call that a transmission gate. Sometimes we draw it like this. Sometimes you'll see it drawn like this. And what I like to draw it as, I like to just draw it like this. So I'll put that there. And I'll just normally assume that the PMOS is there and it has the opposite signal, okay? Just for simplification. But that's called a transmission gate.
So would this effectively be a tri-state buffer?
No. We'll talk about tri-state buffers. It's part of a tri-state buffer, but it's not a tri-state buffer.
Okay.
It's not a buffer because, good question, because a buffer looks like this. 2 inverters back to back is a buffer.
Right.
We learned that last day, right?
Yeah.
And very important difference here. It's a good question. So this is like inverter, and then we say, oh, let's just call it a buffer, no inversion, right? But this thing, say we have a capacitance here, it's driving current onto that capacitance, or it's sinking current from that capacitance. The transistor is driving it to power supply. Whereas in a transmission gate, I'm just going to use the simplified version here. Even when it's turned on, it has some resistance. And so if, let's say I had an inverter driving this transmission gate and some capacitance, what you'll see is this looks like an R and a C, and you'll have an RC delay. So if you have a nice sharp signal here, this one will be a little bit delayed. It'll slow it down. So the transmission gates we're going to see is very effective at generating logic with it, but it's got a drawback, particularly if you put a bunch of transmission gates in series like this. Oh, it gets terrible. You really can't do that. If you put more than one, you start getting all these RC, and then this node up here starts looking like crap. It's slow. We're the picosecond generation, or you are. You will quickly become nanosecond people if you do something like this, okay? So, whereas if you make inverters, every time, like it's drawing capacitance, it's okay because, this was a sharp signal. There might be a little bit delay, but then it gets squared up again. So the delays never cascade when you have a bunch of CMOS gates in series, whereas
Okay.
transmission gates, they do.
Okay, cool.
Yeah.
Thank you.
So yeah, so here's our transmission gate. We've got a P and an N. We connect them together in parallel. We drive them with the opposite signals. And if you look at this by itself, you can write an equation for it. It says basically if S equals 1, so if this S is 1 and the S bar is 0, then Y equals X, right? The output is equal to the input because you got a closed switch. Make sense? And now if I take two of these, let's put two of them in parallel. I have a transmission gate here and transmission gate here. Excuse me. And this one on the bottom, I drive its NMOS with S bar and its P with S. And the one on the top, I do the opposite. I drive its NMOS with S and its PMOS with S bar. And I have X and Y signal here. And now I say, using the same analysis here, well, basically, if S equals 1, the X path passes through to the output, right? And this one's closed and this one's open. And if S equals 0, then the Y passes through and the X is blocked. And we can write an equation. We say if S equals 1, Z equals X, else Z equals Y. Or we can write this in logic. We say Z equals S and X or S bar and Y. So we've formed a 2-to-1 multiplexer. That's a 2-to-1 mux with two transmission gates. And those two transmission gates would take 1, 2, 3, 4, and then we need S and S bar. So we do need a little inverter here. We need an S and an S bar to generate that. So 6 transistors. We can make a 2-to-1 mux with 6 transistors. If we were to go back to basic gates, how would I make a basic? I want to make. This is my 2-to-1 mux here. I'm going to draw. Often we draw muxes like this, right? With these sort of rhombus shapes or whatever you want to call them. X, Y. What did I call it? The output? Z. And the control signal S. If I wanted to make this 2-to-1 mux with basic gates, how would I do that? The most efficient way to make it.
2 AND gates and an OR gate.
I would say what?
2 AND gates and 1 OR gate, and then have one of the ANDs be inverted.
So you want 2 ANDs like this.
And they both connected to an OR.
I connect to an OR. And I would have X and Y, and then I need a S and a S bar. Right? And
Yeah.
that would be Z. So you just made this. How many would have this have? How many transistors?
So 6.
6,
18 total.
6, and 6. 18.
And the inverter.
Oh yeah, plus 2. 20. 20 transistors. We built the other one with 6. So this is more than 3x more. Can I build this better than this though?
Yeah, you can use NAND and NOR.
NAND and NOR? So you want to build it with a NAND? How would, well, what I'd first do, if it was me, I'd kind of demorganize this one, right?
Mm-hmm.
Let's just do that. Let's demorganize that. So how do I demorganize that? What's it become? What's the OR become?
The OR becomes an AND.
Comes a NAND?
And I think the inputs are inverted as well.
Right. It looks like that, right?
Mm-hmm.
So now I have this. Right?
So
And what do I do with these bubbles?
you just push them back and then you
Yeah,
get
I just push them back, right? So in fact, I have 3 NAND gates, right? And an inverter. So now what do I have? What's this one? How many transistors?
4.
4 here, 4 here, 4 here, and 2 there. So now I've got 12 plus 2 equals 14. Well, it's a lot less than 20, but I'm still 2x, more than 2x, right? Than the transmission gates. So this is the most efficient and fastest way to build a 2-to-1 mux with using basic gates, but I'm still more than twice as much as a transmission gates. So transmission gates, super efficient in terms of logic, but they have this drawback I told you, right? You can't make these, you can't kind of cascade them because you have this resistance you're going through. So they slow things down. You can't have basically any more than one. And even one path, it's going to slow things down. So we like these transmission gates for simple circuits that are super efficient. If we need, it's like writing our assembly code. We might use this in some little assembly thing that makes if we have a whole bunch of muxes, we can build them all in of this form, but got to be very careful. Here's another transmission gate circuit. I'm going to leave this for you to figure out for next day. This is a question. I'm going to ask this as a bonus question next day. So you might want to figure it out. What is this logic function? It's using transmission gate logic. Okay, now we're going to go to bonus time. It's bonus time, and let's see who we're going to go.